Hello everyone, my name is Sani Aji from the Department of Mathematics, Faculty of Science, Kim Mongkut University of Technology, Tamburi, Thailand. And I'm here to present our joint work titled Automatic Classification of Low-Angle Fuze-Quick Craters using Deep Learning. So this is the outline of my presentation from the introduction to the conclusion. Low-angle Fuze-Quick craters are artillery craters that are caused by the explosion of low-angle Fuze-Quick projectiles. These craters are characterized by the movement of the projectiles in low angle and their explosion immediately they hit the ground. This makes them to have a distinctive arrowhead shape, which points to the direction from which they are fired. So in this figure, this is the shape of the low-angle Fuze-Quick craters we are talking about, and it has four important parts which are very useful in its analysis. These parts are the center of crater, this one, and point of entry, the two side sprays, and fuse furrow. And in this image, we can see the sample of how these craters appeared in our data set. Crater analysis can be used for precaution and investigative purpose. For precaution, for example, it can be used to identify the suspected locations of hostile weapon and in detecting the presence of other enemy ammunitions. And for its investigation, crater analysis can be used in order to understand the direction or to trace the direction from which an artillery weapon is fired. So, for example, if a country, let's say country A, is having conflicts with two or more other countries, say B and C, so when this country A is attacked by some artillery weapons, and it wants to understand from which of the two countries this attack was, crater analysis can be applied in this aspect. There are two manual methods involved in classifying and identifying these types of craters, as well as measuring the direction from which they are fired. The first one is the fuse furrow and center of crater method, and the second one is the side spray method. Both of these methods involve using compass and stakes manually. However, the manual methods have some limitations. They are prone to errors and they consume a lot of time. Also, information tend to be lost because craters exposed to weather and personnel deteriorate in their values as a source of information rapidly. So, looking at the distinctive features and shapes of these low-angle Fuze-Quick craters and the manual method used in their analysis, and the recent advancement in computer vision and deep learning, our aim is to try to automate this manual process to try to see if we can be able to use computer vision methods in order to automate the manual methods. So our main aim is to classify, localize, and compute the trajectories of these craters. However, in this work, we started with the classification. So we are investigating whether it is possible to accurately classify these low-angle craters using computer vision methods. And the methodology used in this work is that we employ the idea of transfer learning due to the limited amount of the data set. So specifically, we used three residual network models, ResNet 50, ResNet 101, and ResNet 152. So these pre-trained models are used for feature extraction, and subsequently, the extracted features are fed into a support vector machine for classification. The data set used in this work is obtained from an open source GitHub repository and is uploaded by Rudiment, which is a non-governmental organization for human rights research. The dataset consists of satellite images of craters, and for the non-craters, the non-craters are also satellite images, which consist of very confusing objects that can be easily confused by human beings as to whether they are craters or not. These objects includes things like stumps, hulls, decayed grasses, and other environmental portals. So in these two figures, we show the sample of the data set. This is the positive samples, the craters, and this is the negative samples, that is the non-craters. So after collecting these images, we crop them into pieces so that each crater will be in a single image. We also performed data augmentation in order to increase the amount of the data set. We specifically rotate them through -10 to +10 degrees, and we also perform some vertical and horizontal flips. We also did center cropping. And for the feature extraction, the features are extracted by passing the images through the ResNet models during the forward pass. And the output of the last average pooling layer is what we use as the features. So these extracted features are fed into a support vector machine for classification, meaning that the fully connected layers in each of these three models are discarded. And for classification, as I said earlier, we used a support vector machine for the binary classification, and the labels +1 and -1 represent crater and non-crater respectively. And the classifier is learned such that this equation holds. Our experiments were done in 2 steps. The first one, we did not do any data augmentation, while for the second one, data augmentation is performed. And these are the results obtained in both the 2 experiments. The first one is without data augmentation, and the second one, data augmentation is performed. In order to further evaluate the classification performance, the precision and recall metrics were also calculated, and this table shows us the result. From the tables above, it is observed that the classifier achieved more than 95% accuracy despite the challenging nature of the dataset. Despite the challenging nature of the negative dataset, as I explained before, but still the classifier was able to achieve more than 95% accuracy. And we can see that from these 2 tables, after data augmentation, the result, the classification accuracy is also improved. From the result obtained, we observe that this approach can be used in order to classify low-angle Fuze-Quick craters instead of using the manual methods. And this is one of the aim of the work, to see if we can be able to automate the manual methods by using computer vision methods. For future, we can stick to ResNet 50 because, as observed here, both without and with data augmentation, almost all the 3 models used for feature extraction performed similar. The accuracy is similar. So in the future, we can decide to restrict ourselves to ResNet 50. That is, to stick to ResNet 50 for this particular problem, since the difference in performance on this data set is not significant. And this approach finally can serve as an alternative to the manual crater classification. This is the end of my presentation. Thank you very much for your attention.